Okay, thank you very much, Gabriel. Uh, I'm very pleasant to be here in this seminar. So thank you very much for the invitation. In this talk, I would like to summarize some results that we have obtained in the last 10 years about the application of different control approaches for industrial reactors. So the control scheme that we have used in this last year is the following: is the classical hierarchical control architecture, where we have a low-level layer, which is focusing economical aspects, biomass quality or water quality, in case we are working in wastewater treatment. And also we have low-level layers, which are just directly connected to the reactors in such a way that we are working in time scale of seconds and minutes. And of course, we have developed different type of model approaches for the different layers and different control algorithms. I will show you some results for these different layers, but at this point, I would like to emphasize the importance of the low-level control with the following metaphor. Imagine that we have a Formula One car, so we can have a very nice engine and very nice aerodynamics, but if we don't take care of the tires of the car, the performance of the car is not going to be very good. From our point of view, is the same when we are in the reactors. We can propose very nice, very relevant objectives for a high-level point of view, but at the end, if we don't take care of the most important variables, which are directly connected with the microalgae growth rate, at the end, we will not reach the final goal that we follow with the global control architecture. For that reason, I will focus mainly in the control of the temperature, pH, and dissolved oxygen variables. And actually, if we take a look to the microalgae growth rate model, we can see that those variables, as we saw in previous talks, directly affect to the microalgae growth rate, and of course, then to the productivity, in such a way that if we are able to keep these variables close to the optimum values, we will improve the final productivity in the process. But it's not only important when we work with microalgae in clean water. When we work also in wastewater treatment, it's interesting to see how these variables also affect to the bacteria growth rate. So we can define different kind of objectives, just trying to optimize the values of temperature, pH, and dissolved oxygen. So all the results I will show you later on have been evaluated in different types of reactors that we have here in Almeria, and always in outdoors conditions. So starting with the low-level control, the temperature, pH, and dissolved oxygen, which are the variables I will be focused. The idea is that we would like to reach the optimal value for temperature, pH, for the strain we have in the reactor at that moment, and also to avoid that the dissolved oxygen is above the critical limit for the microalgae growth. And then we will develop different control approaches just to be able to keep these variables close to the optimal values. So let's start with the pH control. From my point of view, it's a tricky and funny problem at the same time. We have developed many different control approaches to keep the pH around the optimal value. But here I will just show you some of them. If we take a look to the results, classical results of an off-on controller, we can see here the behavior of the pH, where we see that when we inject CO2, the pH decreases, and then when we stop injecting, because of the photosynthesis phenomena, the pH increases again. So we are fighting all the time with the behavior of the pH, which is very interesting from a dynamics point of view, because it strongly depends also of the weather conditions, of course, because of the photosynthesis phenomena. So we can just try to control the pH from different perspectives. So I will just show you some of them. One of them is just considering the nonlinear dynamics of the pH and the relationship of that dynamics with the inorganic total carbon in such a way that we can be able to control the pH value through the control of the inorganic total carbon and by using or trying to keep in the equilibrium of the different carbon sources that we have in the medium. So following this idea, we develop a cascade control approach in such a way that we want to control the pH in the medium through a sliding mode controller, which try to keep the optimal value of the inorganic total carbon that at the end is related with the pH value in the system. So we evaluated this approach in the real facilities, and here you can see how we were able to keep the pH value at the optimum set point all the time. Of course, thanks to keep the inorganic total carbon around the set point that was calculating online using this control approach. The results were very good, but the point was that the consumption of CO2 was high. So, according to this result, we were thinking about in other different solutions, just looking for a trade-off between performance and also running cost, how to reach that trade-off. And for that reason, we started to work with event-based control approaches. And we developed an event-based model predictive control algorithm with the following idea. We know, as we saw before, that we have a optimal value for the pH, which maximizes the microalgae growth rate. However, if we move just around this value and not just think in the exact value of the pH, we can be able to maximize the productivity, but at the same time, reduce the injections of CO2, and of course, then to reduce the associated cost. So the idea is very simple. It's just once we are in that range around the optimal point, we will not inject CO2, we will not generate events, and when we are out, we just inject CO2, and then we provide events to be able to go back to that range. So we evaluate the behavior in a raceway reactor, in a tubular reactors, in a closed reactor. Here you can see the results, where now we can observe how we are not worried about the optimal value, but a range around that optimal value. And because of that, the performance, as you will see now in the numerical results, were kept very close to the optimum, but we reduce considerably the injections of CO2. Here, we make a set of 7 days experiments. Here we compare the solution of just to control the system with a time-based approach, where we try to reach the optimal value all the time. Here is the event-based model predictive control approach and the classical on-off control solutions. We can see here the productivity is practically the same in the case of the time-based and the event-based control approaches, but we reduce the injection times every day. So at the end, the reduction of the CO2 injections were over 30%. So another interesting issue in the control of the pH is that when we usually control the pH, of course, during the daytime, because it's when the microalgae are doing the photosynthesis process. But then at the evening, we disconnect the pH control. What happened is that during the night, the pH continues increasing because at the evening, the microalgae continue doing the photosynthesis for a while. And for that reason, and because of the injections of CO2 that we did just before disconnecting the control approaches, the pH increases during the night, as you can see here in these results and in these other pictures. So because of this, every morning we had to inject a lot of CO2 to decrease the pH value every morning, and you can see here. But also it wasn't good for the microalgae performance, because the pH was changing to high values every evening and every night. Because of that, we obtained different models trying to control the pH also during the night with just a few of CO2 injections, in such a way that the objective was to keep the pH value close to the optimal reference every night. So we combine this idea with the event-based control approach that I showed you before, and we obtained these results. As you can see, during the night, we just applied a few CO2 injections just to be able to keep the pH close to the optimal value. Because of this, the pH value is not reaching high values anymore, and also we are close to the optimal value every morning, as you can see in these results. So the improvement was very nice. Here is a comparison of classical on-off controller working only during the day. Here is the proposed event-based control approach. As you can see, the injection, here we are controlling the system 24 hours. And injection time is practically the same in comparison with an on-off controller, which is working only during the day. But the productivity was considerably improved. So regarding the dissolved oxygen, the idea is just to avoid that the dissolved oxygen is above the maximum limit. So classically, what is done in the reactors is just to inject a specific air flow in order to decrease the dissolved oxygen in the medium. And sometimes we are just spending so much flow. So what we tried was the following. We used a model that was developed in our group in such a way that it was demonstrated that the mass transfer coefficient is not constant along the day, but it's variable. It can be related with the air flow. So according to this model, we compare the classical control approaches, as I mentioned you before, which is, okay, when the dissolved oxygen is above the limit, we inject a constant airflow to the reactor. And then this solution was evaluated and was compared with the following one. The idea was now to estimate the mass transfer coefficient online, and then to relate this value with the airflow that is needed in that moment to the reactor in order to decrease the dissolved oxygen. So we don't have just anymore a constant airflow, but it's variable along the day according to the mass transfer coefficient changes. So we compare the result with the classical control approach. You can see here a constant mass transfer value and the variable one. We made a simulation comparison first, where we realized that we were able to save more than 20% of airflow injections. And this approach was also evaluated in outdoor conditions, and the results were very promising. As you can see here, we were able just to be at the maximum value most of the time without using a constant airflow as control signal. Another interesting result was the combination of pH and dissolved oxygen and control. As you know, typically the injections are done in the sun. So we are not able to inject both gases at the same time because the performance can be considerably reduced. So for that reason, we developed which is called a selective control approach, in such a way that once we are injecting CO2, we are not injecting air and so on. So we combine this idea with the events-based control approaches that I showed you before. And here you can see the results, as we are able to keep the pH in a certain range, but at the same time, we are keeping the dissolved oxygen below the maximum value. And in the control signals, it's possible to observe that the two gases are not injecting at the same time in the sample. Using this approach, actually, this is the approach that we usually have in the reactors all the time, and the productivity is increased more than 20% in comparison with a classical on-off solution, which is typically used in industry. Regarding the temperature control, we have followed an approach very similar to the one presented by Olivier in the work that he mentioned before. The idea, again, is to use a thermal model of the reactor that was validated for a whole year in Almeria. And then we develop a model predictive control approach to regulate the culture depth by modifying the harvesting and dilution rates. So the idea is very similar. I mean, we use the weather forecast as inputs to the model predictive control and the nonlinear model that I mentioned you before. And then we determine the culture depth in any moment with a resetting horizon approach. So here is a very simple comparison for a strange where the optimal value is 28 degrees. You can see the solution in red color for a fixed value of the culture depth. We can see how the temperature is getting high values. However, thanks to this approach, we modify the culture depth in any moment, and we are able to keep the temperature very close to the optimal reference. And here is a comparison of the temperature index, which is used in the growth rate model. With this approach, we are most of the time close to 1. So we are maximizing that term in the system. So finally, I would like just to show you a couple of examples of the complete hierarchical control architectures. The first one was a solution that we proposed for closed reactors, tubular reactors. The idea was to propose a hierarchical control architecture to maximize the selling of the biomass productions, of course, considering the associated running costs. And then we wanted to optimize the pH value every time to reach this high level objective. So we evaluate the performance by several days first in simulation, where now the optimal value of pH is not constant anymore. Its range is changed inside of a certain range. And the result was very promising in the real facilities, as you can see here. We compared the result with a single layer solution. In simulation, it was interesting to see that we kept more or less the same productivity and we reduced the cost. But when we evaluated this solution in outdoor conditions, in the real reactors, the productivity was also increased. So we were able just not only to increase the productivity, but also to reduce the running costs. As the last example, it was just an idea of a nonlinear optimal control approach to optimize the harvesting in a tubular reactor. So the idea was just change the way of the harvesting in such a way that instead of use a classical harvesting approach, we just try to determine the moment of the day where the harvesting is needed. Or also in the other approach was to not fix just the amount of the harvesting in a specific moment, but also vary just to adapt this harvesting along the day. Okay, so we evaluated these two approaches in the real facilities. And they performed also very well, and we were able with two of them to increase the productivity in the real systems. As future objectives, we are now working also with this global aim, where the idea is just to combine all these experiences in the control approaches for photobioreactors in such a way that we want to reach the industrial demand. And according to the industrial demand, we will determine which type of reactor we need to use and which type of control approaches are necessary just to fill those demands. So finally, I have to say that all these results are not only mine, it's the result of a very nice teamwork that we have here in Almeria. And that's all from my side.